Hello everybody, my name is Vedant Joshi and today I'm going to be talking about a really fascinating concept in the field of computer vision. But before throwing all this mathematical jargon on top of you, I'm going to ask you to take a moment and observe the two objects which are currently visible in your video frame. Now one thing which you might have certainly observed is that I am standing in front of the whiteboard, but there's a slight catch to it. Now, if you're watching this lecture on a 2D screen, then the pixels which are representing this whiteboard and the pixels which are representing me, both of them are equidistant to your eye. But still, you were able to agree with my previous statement. This was possible because your mind knows that the objects which are usually present in the front tend to occlude the objects present behind. And the principle of occlusion allowed you to come to a conclusion that I am standing in front of this whiteboard. This is just one of many depth-related patterns which our visual system is able to extract from the pictorial data, and combine this with our stereo eye setup, we can easily perform the task of depth estimation. So when defined formally, depth estimation is all about recovering the lost three-dimensional depth information by using only the insufficient information present in the 2D images. So given an arbitrary point in an image, 2D image, we try to find its original location in the 3D space. But to truly appreciate this inverse mapping problem, we first need to understand that how a point in a 3D space gets projected onto an 2D image plane. This can be explained by the forward imaging model. Now the forward imaging model can be broken down into three main components, that is W, which is the world coordinate frame, C, which is the camera coordinate frame. So both of them are three-dimensional coordinate frames, and C is nothing but the measurement of the points with respect to the camera. So as if the camera is the origin. And lastly, we have I, which is nothing but the image plane, in which you need to remember one thing, is that the origin is located at the top left corner and this two-dimensional in nature. So in order to define the mapping of point P from 3D to 2D, we need to perform two operations. One is the coordinate transformation and second is the perspective projection. So let's start with perspective projection. Now we define 2 points for perspective projection, that is XC and XI. XC is the location of point P in the camera coordinate frame, and XI is the projection of point P on the 2D image plane, where U is nothing but the X offset in the pixel space and V is the Y offset in the Y pixel space. But one funny thing which you might have noticed out here is that in order to represent a two-dimensional point, I'm using a three-dimensional vector, and in order to represent a three-dimensional point, I'm using a four-dimensional vector. Now the reason why this is done is that we are making use of the homogeneous coordinate system, which allows us to represent all the perspective projection equations in an efficient format of matrix multiplication. So as you can see that we have a homogeneous coordinate format of the camera coordinate system, which gets multiplied to this funny looking matrix in order to give us the values of U and V hidden in the XI. Now this funny looking matrix is called as the internal parameters of the camera, or intrinsic matrix. And in this intrinsic matrix, you only need to remember 4 values. That is Fx, Fy, which are the effective focal lengths in the X direction and the Y direction. And OX and OY is the location on the image plane where the optical axis pierces this plane. Now once you have this mapping available, before that you need to perform a task of coordinate transformation, which is quite simple to understand. Now in coordinate transformation, assume that my right hand is the world coordinate frame and my left hand is the camera coordinate frame. We just need to know 2 points of information. One is, by how much do we need to translate our world coordinate frame to overlap the camera coordinate frame, and by how much do we need to rotate the world coordinate frame to perfectly match the camera coordinate frame. So the translation is denoted by the values of Tx, Ty and Tz vector, and the rotation is denoted by all these R values, and these R values forms nothing but the rotational matrix. And when we combine them, thanks to the homogeneous coordinate system, into a single matrix, these are called as the external parameters of the camera, or the extrinsic matrix, which can be reduced finally onto this equation. So combining these two operations and summing up the whole forward imaging model, we can represent this whole thing in just one equation, which is just this one. In this one, we have the world coordinates in the homogeneous format getting multiplied to the extrinsic matrix, followed by another multiplication to the intrinsic matrix in order to get the homogeneous formats of U pixel and V pixel, which completes our mapping. Now, just as an additional note, these two matrices at the start of the experiment were unknown, but thanks to various camera calibration techniques, we can easily find the values of all these variables of fx, fy, ox, oy, t's and r's, which will completely set up our camera, and we call this as a completely calibrated setup. So lastly, once we have a calibrated setup available to us, we can perform our stereo vision matching. So in the stereo vision, we have two identical cameras which have almost the same calibration, in fact exactly the same calibration. And if we take a point L, UL on the left image plane, then we need to find the corresponding matching point on the right image plane. And once we have these 2 points available, we generate a ray going to infinity from both these planes, and the point at which these two rays intersect is known as the location at which the point UL is found in the 3D space. This is known as the triangulation technique, and the amount by which we shift the identical camera is known as the baseline. Remember, the shifting is only done in the x direction. That's the reason why UL and UR are basically 2 points which have slightly different equations, whereas VL and VY have exactly the same equations. Now these are nothing but the perspective projection equations getting multiplied and finally represented in a normal format. And once we solve these equations, we get back the values of xc, yc and the hero of our discussion, zc, which is nothing but the depth value. Now one thing which you need to remember is the difference between UL minus UR, that is the x coordinate in the left image plane and the x coordinate in the right image plane. This is called as disparity. And in order to truly appreciate this whole stereo setup, you need to understand what disparity and depth have. As it is clearly visible that these two are inversely related, but in order to truly appreciate it, I'm going to give you a small experiment. Now take any object of your interest and cover your right eye and just see it from the left eye and remember this image. Once you have this available, then just cover your left eye and try to remember the right image. And when you compare these two images, since the object was close to you, the images would look quite different. But if you keep the object farther away, the difference between these two images starts to reduce. Therefore, here comes our relation that disparity, lesser the disparity, more is the depth, whereas more is the disparity, lesser is the depth. This is how our brain is able to comprehend the two views coming from our eye and thereby calculate a depth estimation which allows us to safely navigate the environment in which we live.